Are these like lectures related to what we talked about? Yes. So, yeah, these lectures are very tightly related to everything that we've talked about before. Statistics being a branch of mathematics, it builds upon earlier concepts. So if you are having trouble with the previous concepts, you need to try and get the things down. There are a lot of people did really good on the multiple choice part of the test, but for the like calculation part, people just bombed. I was blown away. The highest score was a 76, which is really not that great. Compared to everyone else, it was fantastic. The next highest score was a 60. So from 60 to 76, wow. Whoever did that, congratulations. Anyway, there are a lot of people who got like 30s or worse on a computational part. So why is this? There could be a number of reasons. One, maybe people just were tired, they didn't want to finish the exam, they wanted to have fun because it was Friday. Maybe. Two, maybe people didn't understand some things. The core things that people need to understand have to do with distributions. We're going to be dealing with distributions in the future. We dealt with distributions in the past. All we're doing for a lot of the things is chopping up the distributions. We have some alpha, we want to find the critical value. Well, that's the value that chops off that end maybe, and this end maybe if we have a two-tailed test. Okay, so we find our critical values. Then we can compare our sample mean to what we have as our critical values, and then we're checking that. Okay, then we want to calculate power. So we have another distribution with now the sample mean as its mean instead of the population mean. And we say, okay, well, power, that's the probability of correctly rejecting the null. Well, we reject the null, we had some critical values that we calculated. So the power is just, again, cutting up the distribution based on those previous critical values. You want beta? You're using the same critical values once again, except you are getting a different piece of the distribution. If you have a one-tailed test, maybe you're only looking at this side, but all of these things is just taking some probability distribution and hacking it up into different pieces. The bad way to try to prepare for the exam is to memorize every formula that you need for every situation. Okay, with a one-tailed hypothesis where the sample mean is above the mean, we're going to calculate power this way. You have like a whole bunch of things to remember. But if you just remember what the distributions are and how to cut them up appropriately, then you can use the formulas to figure out what any of those pieces are. P-binom, or not P-binom, P-norm for the normal distribution. If you use P-norm appropriately, you can get any piece that you want. We're going to be cutting up distributions, not today. Tomorrow we'll start cutting up a new distribution. But before that, let's talk about estimating parameters, parameter estimation. So, in previous classes, we've said things like the following. This is the population mean. We have IQs. The population mean is 100. We also say that something else is the population variance. Okay, we're dealing with IQs, so the variance is going to be 15 squared. And I'm giving that to you. Here's the population mean. Here's the population variance. And a couple people have said it at different times, like, wait a minute, but what if we don't know the population? Right? Like, how did you come up with that? Where did you get that? And I said, hold on. Right now, just assume that we know it. Today we're going to talk about the situation where we don't know. We don't know the population. Maybe we don't know the population variance either. So what we want to do is try to figure out what those parameters are, because we need those parameters to answer questions like this, right? Okay, so in order to estimate parameters, let's start with the population that we know about. A population where we say what the mean is and what the variance is, and then we'll derive statistics from a sample. We'll just sample from that population, and then we will calculate the mean that we get for the sample and the variance that we get for the sample, right? Now remember back when we were talking about power, and I said some specific alternative hypothesis? And I said use the best estimate that you have for the mean for that specific alternative hypothesis, right? And the best estimate of the mean, I said, was just the sample mean. Today we'll see if that's true. So we'll see how the statistics, how the mean is distributed. We'll see how variance is distributed. These are sampling distributions. We've already talked about this sampling distribution of the mean, which we needed when we were calculating the standard error of the mean. All right, and then we'll use this information to create estimates. Sometimes we'll already have a good estimate. Sometimes we might need to change what we're doing in order to come up with a good estimate of some population parameter. Okay, so here's some hypothetical population. Imagine it's normally distributed. Imagine it has a mean of 65. Imagine it has a standard deviation of 10. Okay? So we can use our norm. Our norm is a function that randomly selects values from some normal population if you give it some parameters. You can tell our norm how many observations you want. That's like the sample size. You can also tell our norm what the population mean is. Here, population mean is 65. The standard deviation, you can also tell our norm. You have to tell our norm. Here we're saying that it's 10. All right? So if we do this, let me jump into R for a minute. So I said n equals 48, so we're going to have a sample size of 48. Our norm, let me just get one value from, what was the mean? It was 65 and 10. So our norm is just going to take one observation from that population. Boom! All right, so it got 57. We can do it again. Boom! Okay, got 65. We can take another one. Boom! 56. Take another one. Boom! 78. We can use our norm to randomly sample from this population. So now let's do a whole bunch of them at once. So scores equals our norm, 48. So I'm taking here a sample size of 48. And the mean is 65, and the standard deviation is 10. So now if we look at scores, I should have 48 of them. Oops. Scores. Boom. There are our scores. Some are high, here's 71, some are low, we've got a 40 over here. But they should be normally distributed. And we can check this out if we want. Hist, scores. Hey, why doesn't it look perfectly normal? Because of the real limits? Perhaps. Someone else said something else random, I heard. We're randomly selecting, right? We've only taken a sample size of 48. So this isn't a huge sample, right? And the law of large numbers is going to kick in when we take a really large sample. Let's take a really large sample for a second just to verify this. So we go back up here, and instead of taking 48, let me take 4,800 scores. Oh my goodness, that's a lot. Great histogram. Oh, that's much more normal looking. Unless we take an infinite sample size, we're not going to have exactly the normal distribution, but we'll get closer and closer and closer. Anyway, so what I did is I just calculated some scores. I have a bunch of scores. Now, what I can do is I can calculate statistics using those scores, right? So how do I get the mean for those scores? You can tell me the R formula or the regular old formula. It's a sum, right? So the sum of what? The sum of the scores divided by n, right? Yeah. So, boom. If you're using R, you can just say mean scores, which does this. All right. We can also calculate the sample variance. What's the formula for sample variance? Sum x minus the mean. Squared. No minus 1 here. Just n for right now. Right, this is the formula that we said calculates the variance. Right? We'll get to n minus 1 in a little bit. So if we do this in R, we can easily calculate the variance for any particular sample that we have. Now, what if we didn't know what our population mean is? What's our best estimate? So what do I say is our best estimate of the population mean? The sample mean is the best estimate of the population mean, right? Now, the sample mean here is 64.96377. Probably goes up more. Is that 65? It's pretty darn close, right? If we took a larger sample, we should probably be even closer. But there's going to be some variability, right? So the sample mean is our best estimate. Now, let's use R to demonstrate this. The sample mean is really a good estimate of the population mean. So we took one sample previously, right? Took a sample size 48, and then I ended up taking a sample size 4,800. But let's take a whole bunch of samples. We'll create a sampling distribution of the mean, just like we did when we were figuring out the standard error of the mean. So let's take the mean of a whole bunch of samples. To do this, we can use this function called replicate. So replicate, what it does is it does some function the number of times you tell it to. So I'm saying replicate 10,000 times. I want you to get me the mean of, what's this R norm 48, 65, 10? Give me the mean of one sample, size 48, from that normal distribution. Does that make sense? So I'm going to get a sample mean for one sample, and I'm going to get another sample and take the mean of that. I'm going to get another sample. I'm going to end up taking 10,000 samples, each is size 48, and getting the means for those. All right, so let me grab my code. I want bars, I want means. So, not sure if I have all the variables in here. Oh, looks like I do. Cool. Oop, nope, that's wrong. All right. The population mean, what is that? 65? Population standard deviation is 10. And n, is that there? No, n equals 48. All right. Now I should have 10,000 means. So let's get the length, make sure I do. Yep, 10,000 means. We can take a look at some of the means. Let's get the first 10. So notice that with the sample size 10, a lot of our means are pretty close to what we would expect. So the true mean is 65, right? Here we have 65.06, 65.8, 64.4, 63.4, 66.7. So we're getting variability, right? There's some variation. Each sample that we're taking, we're coming up with a different estimate of what the true population mean is, okay? But what would happen in the long run, right? If we were to take lots and lots and lots of samples, what should the mean of all of these sample means be? If the mean of all of these sample means is the population mean, then we know we have a good estimate of the population mean. Does that make sense? It said mean a whole lot in there. So we take one sample, we get the mean, and we say that that's our best estimate, right? Now, if it really is a good estimate of the true population mean, then when we do this again and again and repeatedly observe our sample means, on average, they should be pretty close to the real mean, the true population mean. So I have 10,000 means. Let me plot all 10,000 of them. Boom, there we go. 10,000 means it's distributed like that. It's pretty fairly normally looking, normally distributed looking, right? Okay. So we have a whole bunch of these, and here's a sampling distribution of the mean. This is a little bit different from the one that I just calculated in R. Why? Because I had a different 10,000 replications of sample size 48. So each time you do this, you can have some variations. So if we look at the histogram, what does it look like the mean of all of these means is? 60? It looks like it's at about 65, right? So about in here, right? Now the true mean is there, 65. Where is the mean of all of our 10,000 sample means? Well, it actually turns out that it is so close to 65 that you can't tell the difference. This is actually a red line drawn over the green line, but you can't see any of the green line because the difference is so tiny. So if we jump back in R, so I have all of those means. So let me get the mean of these sample means. 65.025. It's pretty darn close to 65, right? So what does this mean? It means that the sample mean is an unbiased estimate of the population mean. In the long run, the sample means that we get will turn out on average to be the population mean. So in the long run, if we did infinite numbers of replications, the mean of the sample means, it equals the population mean. Exactly. This means it's unbiased. This is a good thing. In the short run though, however, if we take one sample, what's going to happen?
Biased.
It's not going to be biased. The sample mean is an unbiased estimator. But in the short run, each estimate is going to be off. Right? If something is biased, that means that the estimate is off in a particular way. Like it's always greater than the population mean. Or it's always less than the population mean. Or maybe not always, we're talking about probability. So more often than not, it's greater. Or more often than not, it's less than. That's something that's biased. Okay? So each sample mean is going to be off, probably. We're almost never going to see the sample mean truly equaling the true population mean. But one sample mean is going to be above, another one will be below. In the long run, these will cancel out, and you'll have exactly the true population mean. So what do? We have a sample estimate. Right? We have a sample mean. And we want to estimate the population mean from it. But we know that any one sample mean that we observe probably isn't actually going to be the mean. Does that make sense? Any sample that we observe is probably not going to be the true mean. Because it's only when the law of large numbers kicks in, when we have really large sample sizes, when we do things again and again and again, that we're going to find those values converge. But we take a finite sample size, we take 48 people, 48 observations, and we get some mean that probably isn't the true population, right? What can we do? What can we do? If you guys can guess this, I'll be very impressed. What did I say that we do? Again and again? Yeah, so the question is, we observe some particular value for the sample mean, right? And we know, because we've taken statistics, or we're in the middle of statistics, that we're almost never going to find the sample mean is exactly the population mean. It means that the sample mean that we come up with probably going to be wrong, right? But we want to probably be right. What can we do? We can replicate, we can do it again and again and again and again and again. Yes. But in a world where replication can be expensive, you might not want to. Increase the sample size. This is similar to replication. You're basically throwing more data at the problem. This will help, but again, this costs more money. Have to change the... You could change the alpha, potentially. Alpha determines something. What does alpha determine? It determines this region that we reject the null hypothesis and that we fail to reject the null hypothesis, right? Now, what we can do is we can try to create a region that is probably going to contain the mean. I don't like saying it that way, but I'm going to say it that way because I think it might be less confusing at this point. Let's see. So, yes, we're going to create a range. Just like we did when we created this range that we failed to reject. Or I guess the range was actually where we, where we failed to reject. And then beyond that, we were rejecting. So in hypothesis testing, we did this again and again and again, right? We created a range where we failed to reject the null. This was bounded by the critical values. And what we said is that most sample means would fall inside this range if the null were true, right? If the null hypothesis was true, if we had an alpha of 0.05, what percent of the time should the sample mean fall in that range? It should fall in that range 95% of the time, right? Draw our distributions. Here we go. We have some distribution. We're cutting it off. We have half of alpha up here. Okay, alpha over 2 and alpha over 2 down here. What's left? 1 minus alpha. If alpha was 0.05, we've got 95% of the stuff in the middle. Okay, so 95% of the time, the sample mean would fall in that range. Now, here we're going to calculate a different type of range. Here we want a range that should contain the true mean, right? Here we were calculating a range that sample means should fall in. So we had some true mean, or some hypothesis about a true mean, and we were creating a range that the sample mean should fall in. Here we're doing sort of the opposite. We have a sample mean, and from this we want to create a range that the true mean should fall in. Okay? This is a range that we can be confident about. The name for this is a confidence interval. A confidence interval. So how do we find the range? Well, range is just the maximum of some square minus the minimum of some square. So we need to find the maximum and minimum values, right? Now when we did this with hypothesis testing for two tails, we basically just rounded the upper and lower critical values, right? And that range told us when we would fail to reject or not fail to reject. So we could use this in R to calculate those lower and upper critical values. Now, if we want to estimate the means, what do we need to do? Well, we need to create another range, right? But can you guys see that? So we have some distribution. It's centered on our sample mean, right? So X bar. And we want to figure out where that sample, or where the true mean should fall, right? So we can create lower and upper confidence limits. So if we want like a 95% confidence interval, we want some values, that's going to cut off 95% of the distribution in here to 5% over there. That's the same type of thing that we were doing above, right? So take a look at these two formulas. Can someone tell me what the difference is?
One is the parameter and the second one is sample.
Yeah, here. Oh. Here's what I have. Yes! So here, I have the population, the parameter. And here, I'm using, I don't know why those never show up. I'm using the sample mean. What? Everything else is what? Everything else is identical. So if you have the previous stuff down, this is a piece of cake. If you don't, you need to take a look at the previous stuff. Okay, so how do we interpret the confidence interval? Let's say that we want a 95% confidence interval. What does this mean?
There is only a chance that the true mean is out of those.
We want not a 95% chance that the mean is out of those, that the true mean is in those. Is that right? So the probability that the true mean is contained in the confidence interval is 0.95. Now this actually sounds really, really good. But this is actually not completely correct. It's a reasonable way to think about it, but technically it's not correct. And why is this? So we create some confidence interval, right? Now, once we have the confidence interval, the true mean either is in that or it's not. There's no probability. There's no chance associated with it. However, what there is probability with has to do with the number of confidence intervals that will contain the true mean. So 95% of the 95% confidence intervals will contain the true mean. This is very similar to the above saying. The above saying isn't technically right. So the probability of creating a confidence interval that contains the mean is 0.95. Yeah.
Still, I don't understand what's the difference between two.
Can someone explain the difference? Besides me? I had a point in my hand. Or in my pocket earlier? I don't know. Alright, what is it?
X.
The probability of her getting this right is what? It is heads. Now, we just calculated this. What's the probability that this is heads?
1.
Exactly. So with this, we calculate the confidence interval. The population mean, it is what it is. Population mean doesn't vary. There's no like randomness to the population mean. It is something, right? So we would be technically incorrect to say that the probability that the population mean is in our interval is 0.95. That'd be like saying the probability that this is heads is 0.5. No, it's 1. However, on any given flip, we have a 0.5 probability that it will turn out heads, right? All right, so let's do it. Let's create a confidence interval. So we have a normal population. We have a sample size of 48. Standard deviation of 10. The sample mean is 64. So what's the mean? What's the mean? Oh, we don't know. Our best estimate is that it is 64. That's our best estimate. But now we want to create a confidence interval. Confidence interval that if we were to create them 95% of the time, we should have the population mean in there. How do we do this?
Besides replicating?
Besides replicating, yes. Use a formula. What formula? The one I gave, did I give a formula yet? I don't think I did.
We found the confidence interval.
I didn't give a formula for the confidence interval yet, have I?
No, we use score.
We use z-score. That's interesting. Let's take the formula for a z-score. So the formula for z-score is what? Sample mean minus
E
the mean
divided by standard deviation.
Okay.
And divided by square of 10.
Of n, right?
Yes.
Now, so do we have some of this information? What piece of information are we looking for? Looking for this, right?
But we don't have this.
We don't have a z-score. Aha! We don't have a z-score. Did I say, like, let's do it for 95? Yeah, okay. Let's do it for a 95% confidence interval. What z-score is cut off?
1.46, 64.
1.64?
No, 26.
1.96?
That's all 5%.
My common knowledge is failing me. It's like, it's either 1.96 or 1.64.
96 is 5%, 10% is...
All right, we'll take your word for it. We can change this if we have to. All right, it's on the slide in a minute. But let's figure out how we can do this. Okay, so 1.96 equals what? 64 minus, who knows, all over 10 divided by square root of 48. So if we do some algebra, we can multiply both sides by this, right? So 10 divided by square root of 48. Let's do the same thing over here. What happens now? These cancel out. Awesome. What do we do then? Okay, well, let's get rid of the 64. Let's take 64 away from this side. And negative 64 here. All right. And we're left with a negative something, right? So we just take that negative away, multiply both sides by a negative, so we get positive 64 minus that, right? Sweet. So there is a formula that we can compute, like a critical mean, the mean at the top or lower end of our confidence interval. So common knowledge, man, you're awesome. You got it. 1.96 cuts off 95% of the z distribution. So our limits, how do we find them? 64. Well, it's actually plus or minus, right? Remember, the z distribution is normal. It's symmetrical and unimodal. So the z value that we got, notice this is an absolute value. The absolute value of z is 1.96. So here we calculated 64 minus this. So this is going to be our lower estimate. The lower confidence limit, right? So the plus here, that will give us the upper confidence limit. So this is our answer. Our confidence, our 95% confidence interval ranges from 61.2 to 66.8. If we were doing this with R, we just use Q norm. Give it the appropriate mean and the standard error of the mean for the alpha portion that we want, and boom, we've got the lower one. For the upper one, same thing, except now we're using 1 minus that alpha portion, right? Sweet. Now, previously, when we created like these critical values, we used these to test hypotheses, right? We said that when the sample mean fell outside of, or beyond the critical values, what would we do?
Reject.
We would reject. When the sample mean fell beyond the critical values, we reject. Now we have critical values, sort of, except they're centered around the sample mean. So what do you think we might do? When might we reject the null? Now the null hypothesis gives us some mean, right? the population mean, we believe that the population mean is X, right? So when would we reject the null?
According to this correct.
According to the critical values, would we reject when it falls within or beyond? We're going to reject when it falls beyond the confidence interval. So before, when the sample mean fell into the rejection region, we rejected the null. Here, when the hypothesized mean falls outside of the confidence interval, we can reject the null. The true mean would be contained in 95% of the 95% confidence intervals that one can construct. Right? It's 10 times, right? Okay, so tails and confidence intervals. Someone could create a one-tailed confidence interval. If you were creating a one-tailed confidence interval, what would one of the tails have to be? Or the absolute value of one of the tails? Not 0.
Can you repeat the question?
So we have some distribution, right? And when we did a two-tailed confidence interval, we chopped off those and those, right? But if we do a one-tailed, we're only looking at one tail, right? Where does this stop? Infinity. This keeps on going and going and going and getting closer and closer and closer and closer to 0. So, if we have a one-tailed confidence interval, one of the values, at least the absolute value of one of those values, is going to be infinity. Depending on which tail we're talking about, it could be positive infinity or negative. Negative infinity, negative infinity. All right, so for the previous example, let's create a 95% one-tailed confidence interval for the null hypothesis that the sample mean is less than or equal 63. In order to figure out which tails we're interested in, let's first draw the standard shouldn't use standard. Let's draw the distribution for the null hypothesis. All right? So the null hypothesis says that we have a distribution centered on 63, and we're interested in one tail. In which tail are we going to reject? Sample mean is less than or equal to 63. That's saying that the sample mean is over here, so we're interested in this side, right? Okay. So, if that's the case, which tail are we going to be interested in for our confidence interval?
Correct.
So our confidence interval, we have some distribution with some mean, whatever it is. Are we going to put the confidence interval up here or up here? At least the tail that we're chopping off. We're going to put it over here, you said. This one. He looks sort of like, yeah, maybe. Does anyone else agree with him? We got 2 people. Anyone else? Who disagrees? Who's willing to disagree? Nobody. So you all agree with him? You disagree with him? All right. Well, let's think. So if the null hypothesis is correct, we're going to reject the null hypothesis when we observe a sample mean over here, right? Now, if some alternative sample mean is correct, when are we going to reject the null hypothesis? The other one. Yes. Right? But let's take an example. Let's say that this is what we actually observed was 65, okay? 65. So 65, this is actually above the population number, right? I don't know if it's significantly above, we have to compute the standard error, mean, and the rest of that stuff, right? But at least numerically, it's above the mean. So when do we want to reject the null hypothesis? When our hypothesized true mean falls outside of the confidence interval. What's our confidence interval here? Well, it's whatever this is, all the way up to positive infinity. Okay? So we only want to reject the null hypothesis if the true mean falls beyond this. If it really is significantly less than.
Will we reject or fail to reject?
Then when it is significantly less than, then we fail to reject. I'm sorry, we reject.
Why?
Why?
Say that
No hypothesis saying that.
less than 63.
Right. So this is the null hypothesis. Right? So the null hypothesis, we're going to come up with some critical value. Should we do it? Should we find it? All right. So how do we do it? So our population mean, according to the null hypothesis, is equal to, what did I say, 63?
Yes.
Sample mean is less than or equal to 63. So we're going to use 63 as the estimate. All right. Standard deviation. I believe I'm still using, I'm still using the standard deviation of 10. So population standard deviation is equal to 10. What's the standard error of the mean?
10
divided by.
It's the population standard deviation divided by the square root of 48. 48. All right, cool. Now we can use Q-norm. Q-norm, what do we want? Alpha is 0.05.
One tail.
It's one tail.
We want to know the upper tail.
We want the upper tail.
Why do we want to
Why do we want the upper tail? So our null hypothesis is that the sample mean, or that the mean is less than or equal to 63, right? So we want this. This is where we're going to reject it. So that's 1 minus alpha.
1
So 0.95 and the P mean and standard error of the mean. Here we go. So our critical value was 65.37, right? Roughly. So I said we got a 65. What should we do? Fail to reject, right? Why? Because 65 falls inside of this. 65 is like there. We fail to reject. Now, when would we reject? Well, if we had 67, well, that would be out here, right? Then we would reject. So now we said, okay, we have 65. When are we going to reject? We create some confidence interval, and when the hypothesized mean falls outside of that confidence interval, we're rejecting, right? So the confidence interval that we're going to create is going to be from here to here. Because the hypothesized mean is...
Sorry, the population mean, is it in the first one or the second one? Which one are we talking about here? The population, not the sample.
The population. We use the population mean, or the null hypothesis, what the value that it said the population mean would be, to figure out the critical value.
When you gave 65, it's a sample, random sample.
That was some random sample that I took. I happened to get a mean of 65.
We're finding the interval, like the confidence interval for the second one, not the first one.
That's right. We're finding the confidence interval based on our best estimate. So our best estimate of what the true population mean is 65, right? What's our 95% confidence interval of that? Now previously it was easy because we said we had 2 tails, but here we said we have 1 tail. So which tail are we interested in? It's basically just flipping the sign. We're rejecting when the sample mean is over here. We're rejecting when the true mean is over here. He's got it, so can you explain it? Because maybe he can explain it better than I can. Try.
Okay, so in the beginning, you are actually rejecting the sample mean.
Uh-huh.
So the right.
I'm rejecting the sample mean when it's to the right of this.
Yes. So you got, the confidence interval. You have a sample mean, and you want to figure out where the true mean is. So you can't actually, when the true mean is beyond this confidence interval, you will reject it. But the true mean is obviously it's in the other way, because that's where the, how can I say that? I can't explain more. It's in the left way because that's where, I can't explain more.
Because it is about the critical, what we find for true, we will fail to reject. Because we find about what we find. Not the second one. Yeah.
So if we found something over here, let's think about this a different way. Forget the tails right now. But let's answer a question. I just had a massive brain fart. I was like on the right path and then I lost it. Borullo Verde. Okay. So, okay. So, this is our sample mean. Okay? That's what we observe. If the true mean was like 68, would we reject the null?
We're supposed to reject the null.
Huh?
We're supposed to reject the null, yes.
We're supposed to reject the null.
Because
I switch the true mean.
where is the true mean? 63? A population mean.
So before I said it was 63, now I'm saying imagine that it's 68. Okay? So instead of 63, we have 68. So the true mean is 68, right? It's up here somewhere. Now the hypothesis was that the sample mean is less than or equal to some value, right? Here I said it's 68. Is this less than or equal
Yes.
to 68? Yes, it is. Right? It's not equal to, but it is less than. This is less than 68. So I couldn't reject this. Right? I failed to reject it. Could I reject it if it was 108? If the true mean was 108? So the null hypothesis says that it is less than or equal to the true mean. Right? Or that it is less than or equal to 108. Could I reject? No, I couldn't. Is 65 less than 108? It's less than 108. So the only time that we're going to be able to reject a 65 is when it is greater than some hypothesized mean. Right? Here, we're only rejecting when this is greater than some hypothesized mean. Right? So if this is greater than the hypothesized mean, then that means that the critical limit for the confidence interval has got to be less than that. Because it's only when the true mean falls down here, or that our hypothesized mean falls down here, that we would actually end up rejecting it. If our hypothesized mean falls anywhere over here, given that directional of a hypothesis, we will never, ever, ever reject it.
Because we're corresponding to the null hypothesis.
That's exactly right. So, which critical value do we need to compute? We need to calculate The left tail. The left tail. So for the null hypothesis, when we're hypothesis testing using these critical values calculated from the null hypothesis, we would have been looking for the right tail value. But here, when we are testing the hypothesis testing off of the confidence interval, we're going to use the opposite tail. So we're using the left tail here. And then it's easy to compute. We already figured out what, based on the z score, we just algebraically manipulated this. So this was our observed mean minus, because we're looking for the, it should be, right, yeah. We're looking for this tail, the lower tail, so we're taking minus 1.64. Not 1.96 here, because we only want the bottom 5%. We don't want 5% split among both tails, we just want one tail. So times 1.64 times the standard deviation for population, all divided by the square root of the sample size, which gives us the standard error of the mean, and our answer is 61.6. Now, earlier, what did we say that we did? What did we do up here? The critical value was 65.37, and we said we actually observed a 65. What did we do? We failed to reject, right? Now here, what do we do? Well, let's see. So the the confidence interval, so the mean is greater than or equal to 61.6 and less than or equal to positive infinity, right? Where does the hypothesized mean fall? The hypothesized mean was 63, right? So the hypothesized mean is in this interval. What do? Failed to reject. So we failed to reject in both situations. Now, you're not going to be using confidence intervals to test hypotheses because you have these other ways that you can do it automatically. But I wanted to show you sort of what the logic is in the relationship between the confidence intervals and the standard hypothesis testing. So there's our interval. We failed to reject. All right. Here's why you're not going to be using confidence intervals to calculate, to do your hypothesis testing. Typically, you'll never, ever report one-tailed confidence intervals. Why is this? Well, you can do your hypothesis testing in the traditional way. Now, the confidence interval gives us a range, right? That the true mean, I'm going to say it the wrong way here, that the true mean is probably between here and here. It's the wrong way, but. Okay? So, the true mean is within there. Now, think about what a range is. It's the difference between a maximum and a minimum. Well, if you have one tail, then you have an infinite range. That's not really a very good estimate at all. Right? So what do? If you want to create a good estimate and sort of bound what your guesses are, use two-tailed. So you do your regular old hypothesis testing and calculate confidence intervals for two tails, unless I specifically tell you to calculate for one. I don't think that's ever going to happen.
I mean, we calculate two tails even if the null hypothesis is one tail?
Well, so if you calculate the confidence interval for two-tailed hypothesis, you are not going to be able to necessarily reject the null based on the confidence interval, even though you could reject it for the traditional test, based on how much of that percentage or probability you're putting in those tails, right? So in the one case, so this was a 65.37, right? Now our two-tailed, if we were to put both of these out here, imagine that instead of a 65, you've got like a 65.4. Right? It's just beyond. So we're just going to fail to reject it. But if we end up putting all of, or not all of alpha, half in both sides. This will make the true mean closer to the fail to reject region. Yes?
You said when we observe 65.4 something, we fail to reject.
When we observe 65.4, we should reject. We should reject. However, with the confidence intervals, we might fail to reject. Because instead of having all of it in one side, let's say that this was the true hypothesized mean, and this is our one-tailed cutoff. But now by going to 2, oh, oops, we just missed it. So do your hypothesis testing using the regular hypothesis testing techniques. Keep going on. Norm. Don't use confidence intervals for hypothesis testing unless you have a non-directional hypothesis, one that says it is equal without a less than or equal to. When we use confidence intervals? All over the place. In lots of journals, you have to record confidence intervals in addition to the results of your statistics test. So you say, aha, I found the value of this statistic was this, p is less than 0.05, and then you say the sample mean was this, confidence interval that. Or maybe instead of saying what the confidence interval is, you give it the standard error of the mean so someone can calculate the confidence interval. But typically you report that, so that way someone later on who's trying to figure out what the true mean really is, they can use your estimates of the mean and someone else's estimates of the mean, and basically by looking at lots and lots of people's estimates, converging on what that true mean is. It's called meta-analysis, and you're not going to do that in this class. All right, so do your hypothesis testing the traditional way, then report the smallest confidence interval. The smallest confidence interval is the one with both tails that is centered on the sample mean. Uh-oh. What if you don't know the variance? Oh, man. Right? So we just talked about creating a confidence interval that 95% of the time should contain the true mean. What if we don't know the variance either? What do we do? We could create a confidence interval for the variance, right? That's perfect. Now, we're going to have to estimate what the variance is, right? And then we could create a confidence interval for it. Now, we're actually not going to figure out the confidence intervals for the variance. But we are going to do something else. So we said that the sample mean was our best estimate of the population mean, right? And to show this, I did a sampling distribution of the mean. Right? I took a sample, I got the mean. I took another sample, I got its mean. I took another sample, I got its mean. And I plotted all of those means. And I figured out what the mean of all of those means were. So I can do the same thing for the variance of the sample. I can take a sample, I can calculate the variance. I can take another sample, I can calculate the variance. I can take another sample and calculate the variance. And I can plot all of those variances. And I can get the average, the mean variance. And what we want to see is if that mean variance is the same as the population variance, right? If the mean of the sampling distribution of the variance is equal to the population variance, what do we know? We have what type of estimate?
Unbiased.
Unbiased. So we want to see if our formula for variance that we had earlier, which was this, if that is unbiased. All right? So let's do this. For the variance of the sample, we'll use a mean of 0 and a standard deviation of 1. Again, I'm giving you these right now, so we have something to start with. Then we'll sample from that, and we'll work backwards. We'll see if our estimates from the sample actually turn out to be what those things tell us it should be. Okay? So Notice my mean and standard deviation. What type of distribution is this, if this is normal? normal distribution. What type of normal distribution is a normal distribution with a mean of 0? It's a z distribution. It's a standard normal distribution. Okay, so here is the sampling distribution of the variance with a sample size 2 with 10,000 samples. Let's do this in order. So I created a function called myvar to calculate the variance, because remember I said that the R's version of variance didn't calculate that, it calculates something different. So I created my own function, and now let's check this out. Okay, this is done. Okay, so here I set the population mean to 0, the variance to 1, population variance to 1, which means that the population standard deviation is equal to 1. Set that the sample size is 2. So the standard error of the mean is going to be the population standard deviation divided by the square root of n, which is just the square root of 2. And now I'm using this replicate function again. So I have rep myvar r norm n p mean psd. So the r norm, again, n with the mean and standard deviation. This just gives us, oops, mean. Right. So I said n was equal to 2. So I took a sample size of 2 here. Okay?
Why do you use R norm?
R norm is going to randomly select from a normal population. When we did P norm, we were looking for the cumulative probability of a normal population. D norm told us the probability of density for the normal population. R is just taking a random sample. So I took a random sample size 2 from the population. Now if I calculate the variance for that, actually I'm going to have to get a new random sample because I didn't save it, R norm, NP mean, PSD. This will tell us the variance in that sample. And then by replicating it, as I did above, I have now 10,000 estimates of the variance. Lots and lots and lots of estimates of the variance. Now, what I did when I did this for the mean was I plotted the histogram, right? Just of all of the sample variances. Oh, there it is. It's very similar to what was on the slide. A little bit different. Why? Because I'm taking a different random sample, doing different replications. All right. So what's the mean of the variance? Mean of vars, 0.05. 0.05. I'm sorry, 0.05. 0.5. 0.50. You know, when you have a teacher that's slightly dyslexic, it's going to make things more difficult. So my apologies. 0.50. What do we say that the standard deviation or the variance was? 1.
Divided by population number.
So this is like 1 divided by the population number,
Something.
right? Or not the population number, but the sample size, right? 1 divided by 2 is 0.5. Well, it's possible that this is just off because we got a really freaky sample, right? So we can do this some more. Let's get a new value for vars. Here we go. It's a new random sample. Let's find the mean of this. Okay, well, we have a different mean, right? As we would expect, because we have a finite sample size and finite numbers of replications, so no wonder our mean is a bit off. Let's do this again. You guys see a pattern? What is it? These are consistently coming out as about 0.5. About the population variance divided by 2, divided by the sample size, right? Huh, that's interesting. All right, so let's jump back. So here we go. The population variance was this. The mean variance of the sampling distribution, that was when I took mean of all of those, was the one in red. And notice here that the one in red is about half of the population variance, right? Or just the population variance divided by 2. So the mean variance is about half of the population variance. So maybe that's a fluke. We already just saw, I did this like 5 times. You can download the code and do it for yourself 100 times if you would like. It's not a fluke. This is not a mistake. So the question now is, does this pattern hold for other sample sizes? This was a sample size of 2. What if we took a sample size of 3? Well, let's see. Sample size 3. Let me reset n. N equals 3. Oop, not 2, 3. Okay, now the mean was 0.66. Maybe that's just a fluke. 0.68, 0.65, 0.669, 0.68. Does anyone recognize the pattern yet? 0.67. 0.65, 0.66. Is there a fraction that's about 0.65, 0.66? Besides like 66 over 100? 2 divided by 3 is awfully close to that. So with the sample size of 3, boom, there's our population variance, and there's the mean variance of this particular sampling distribution. Notice that when we had a sample size of 2, it was like half. Now it's like 2/3. So the population variance here is about 2/3 of the population. It's not a fluke. Let's try n equals 4. Sorry, n equals 4. Where are we there? Ah, what's that? 0.75. Maybe that's a fluke. 0.76. 0.77 if you're round. 0.74. So with a sample size of 4, we had, again, the population variance was 1, and the mean variance of the sampling distribution now was a bit closer to 1 than it was before. It's about 3/4 of the population. So with the sample size 2, the estimates that we were coming up with, on average, were about half of what the real variance was. With the sample size 3, our estimates were about 2/3 the size of the true population variance. When we had an estimate of 4, we had an estimate that was 3/4. Does anyone recognize the pattern? So when n was 2, we had 1/2. N was 3, we had 2/3. When n was 4, we had 3/4. What if n was 100?
99 divided by 100.
Prediction? All right. N equals 100. So what should the mean of vars be? Close to 0.99. Oh, that's pretty close. Wow. That's kind of cool. So based on this evidence, what can we say about this formula and its estimate of the population variance? Is it biased or unbiased?
Unbiased.
It's unbiased.
Biased when the n is increasing.
When n gets very large, it's actually still biased, but it's very tinily biased. Tinily biased? When n is small, whoa, there's a huge amount of bias. So, we have a biased estimator. In the long run, that's what we did when we took all those replications. We were trying to get at the long run. We didn't really get infinite, we just got 10,000 of them. But we saw that this actually turned out to be 2/3 or 1/2 or 99 1/100ths of the true population variance, right? So this is bias. So how can we get rid of the bias?
What is
S. So S is sample, like, so S by itself would be a sample standard deviation. S squared sample variance.
We divided by n minus 1.
We could divide by n minus 1. So,
Yeah, no. The first one we just divide by n minus 1, yes.
this.
Yeah.
If we divide this, so are you saying like n times n minus 1, or are you just saying
Divided by
n minus 1?
Divided by n.
He's absolutely right. If you just divide this by n minus 1, you can get rid of the bias. So we have some formula, right, for what the true variance is and what our sample variance was. We have a way to relate it. So all we need to do is multiply both sides by the reciprocal of this, right? Multiply n by over n minus 1, that will get rid of it here. So here n over n minus 1 is this. Now if we put the n over n minus 1 here, that gets rid, those n's cancel out, and boom, you're left with n minus 1 on the denominator. That is perfect, that's beautiful. So earlier you said n minus 1. I think this is what you were thinking about. This formula here, with the n minus 1 in the denominator, this is our unbiased estimate of the variance. So to indicate this is our unbiased estimate, I'm putting a hat on it, because it's special. It's like the king. It's the king of our variance estimates. So we'll put this pretty little hat on it, indicate that it's a good estimate. Okay?
Can you give an example?
Can I give you an example? Okay. We have some green one. This actually wasn't that bad. So let's say that our S squared was 24. What is our estimate, our unbiased estimate of the variance?
What's S again?
S is the sample, the variance, or the standard deviation of the sample. So S squared is the variance of the sample, as computed by this formula. So if this is our,
What is n?
N is the sample size.
what is n?
When is n?
Good, we need n. What is it?
Sample size.
Yeah, but what, give me a value. He said that we should do an example, so we're doing an example. We need n. What is it? 3.
So 2.
Alright, so n equals 3. So what is this?
2 divided by 3. No.
3 divided.
We use this one first.
Okay, 3s squared.
Yes.
3 s squared
Divided by 2.
divided by 2. So we have 3 times 24 divided by 2, or that's 3 times 12 divided by 2, 36.
No, not.
No, did I mess it up?
You divide
We
twice.
only divided by 2.
You divide 4.
No, the results of the
Results.
result
That is true, but Yes.
Okay.
Groovy. All right. So maybe we can use our unbiased estimate now. So previously we used the population variance to create a confidence interval, right, and perform z-tests. So if we didn't know what the population variance was, what could we use? What's our best estimate? Our best estimate is the unbiased one, which is the s squared times n over n minus 1, or if you just modify this formula, this. Right? That's our best estimate of what the population variance is. Because when we had n instead of n minus 1, we were really biased. That's not a very good estimate. So now we have an unbiased estimate. This is our best estimate that we have. Okay, so we can use our estimate to do the same. So let's take a look at the sampling distributions of the following. So here I have z squared. Mean, sample mean minus population mean over population standard deviation divided by the square root of the sample size. Now, let's basically take the same thing and put this, which is our estimate, right? This was when we knew what the population variance or the population standard deviation is. But here I said we don't know what it is. So what do we use? We use our best estimate, right? That's this. Okay? So this is our best estimate. These two formulas are exactly the same. You can ignore the t for now, right? Just look at this and notice that the only difference has to do with these two parts. One is the population variance or standard deviation. One is the best estimate that we have for the population standard deviation. Yes? When we want to calculate the mean, we just replace the z with t. Yes, you could do that. But maybe these are actually the same things. Maybe z and t are identical to one another. So I just made a t here, so we had something to test the z against. All right, so here's the sampling distribution of z with a sample size 2. This is just a sampling distribution. We can create a sampling distribution of anything, any statistic that we can compute. So before, I took a sample, I took the mean for that sample. Then later on, we took a sample, we took a variance of that sample, right? Here, all I did was I took a sample, and I took a z-score for that sample. So I did that, then I took another sample. I got the z-score for that sample. I took another sample. I got the z-score for that sample. And I did this 10,000 times. Oh, it's such a nice, pretty, normal shape. Let's take a look at a t distribution. So there's the z. Here comes the t. What?
Why?
Why? Why? That's a really good question. There's only one difference here, right? I mean, if you ignore the z's and the t's for the moment and just look at the rest of it, the only difference is in these terms, right? This here, that's a constant. We're told what the population standard deviation is. Here, what is that? It's something that we calculated from a sample. It's not a constant, it is a non-constant, but there's a name for that. It's a variable. It's a variable. Here, this variable is a constant. Here, this variable is a variable. So, imagine that we have an atypical mean. Imagine that the true mean is 100, okay? Now, if we take a sample of size 2, when are we going to get, like, a sample mean of 50? Well, we could get one of like 0 and one of 100. We could get one of 50 and one of 50. But if it's really an atypical typical value, what's going to happen is that you're going to only get that when you have a bunch of observations that are really far from the mean, right? Does that make sense? When I sample from a population, like sometimes my samples are close to the mean, right? Now, with a sample close to the mean, it could be that I have two values that are both close to the mean. Or it could mean that I have like a value that's really far over here and a value that's really far over here, right? Now, imagine that I have some distribution like this, where values like this are really unlikely. If I had a mean of this, what does that mean? Well, probably I got two values that were really unlikely. And not one that was really unlikely over here, and one that was even more unlikely over here, right? Because that's even less likely. And probably I got two fairly unlikely values, which means that that's going to have a small amount of variance for that sample. Because all those values are kind of close together, which is why you would observe an unusual mean. This will produce a tiny estimate for variance. Right? Because variance is just a spread. So if all of the values are close to one another, you get a tiny, tiny, tiny estimate of the variance. And when you're computing the z's, you are dividing by the estimate of variance. And if this is really tiny, what will happen? This is really tiny. This will be very, very big. Right? So this will make the absolute value of t very large. So notice here, with the sample size 2, like you can't see it because they're so infrequent, it doesn't build up much mass. But we have some value that's way out here. Right? It's a very huge negative value. Huh. Okay. So, we will finish with this on Wednesday.